It says the average electrical power of a solar panel can be approximated with an equation, and P is going to be the percent of the maximum power that you might achieve with that solar panel if it like had 100% sunlight. Theta is the degrees latitude, and so if theta is 0, you're talking about the equator where you get the most direct sunlight, and if theta is 90 degrees or pi halves, then that would correspond to the pole, either the North Pole or the South Pole. I'll write that over here. So theta equals 0 would be like the equator, and theta equals pi halves would be the pole, either north or south, doesn't matter. So the farther away you go from the equator, the less power your solar panel is going to produce. So like solar panels are great for like, Mexico and the southern US, but if you were like up in Canada, you're not going to get direct sunlight as much of the year because the earth is sort of makes you tilt away from the sun, right? And then we have another variable that we call capital C, and that's the fraction of the daytime that direct sunlight is obscured by clouds. So if you live in, what do you call it? Like Arizona, like Flagstaff or Phoenix, like you have like no clouds ever. And so C would be like 0 for Phoenix. But if you lived in Houston, C would be 1 because there's always clouds overhead in Houston. Okay, so the question asks, what is the power output percent? So what is P? When the panel is installed at 30 degrees latitude, so I'm going to say theta is equal to 30. I think this is in degrees, so I should say this is. Okay, there we go. Theta is 30 and C is a quarter, 0.25. So all we have to do for question 1 is plug in those numbers. I have 1 minus pi squared times 30 squared, because theta is 30, divided by 2 times 180 squared, times 1 minus 0.25 over 2 times 100%. And so you just really need a calculator for this. That's the whole trick. Oh, and I didn't pass out calculators today. Oops.
So we have Texas instruments. Do they have like California instruments, Ohio instruments, like dedicated calculators for each state?
No.
So everyone uses Texas instruments?
Nice.
Unless they
Texas
use
is the best in the world.
unless they use a Casio.
That's actually something that I've never noticed.
What's ridiculous about these calculators is that the price of the calculator keeps going up even though the technology keeps getting older and older and older. Right? Like typically, like the price of TVs continues to go down every single year. You can always get a bigger and bigger TV for less money at Walmart every year, but the price of calculators goes up, even though this is the same calculator they were using 40 years ago. Okay, so we have 1 minus pi squared. So we do pi squared times 30 squared divided by 2, and then divided by 180 squared times, open parentheses, 1 minus 0.25 divided by 2, close parentheses, times 100. And so that's going to be 75.5%. Okay. So if you were at like 30 degrees latitude, which is about where we are, not exactly, but it's about there, and there was cloud cover a quarter of the time, then this approximation formula is saying that your solar panel would get about 75% of the power that it would, if it were situated at the equator with no clouds. Okay, question 2 says, determine the equation for the contour lines corresponding to p is equal to 1. Well, if p is equal to 1, I'm just going to rewrite this formula up here, but then replace p with 1. So I'll say 1 is equal to 1 minus pi squared theta squared over 2 times 180 squared times 1 minus c over 2 times 100%. By the way, 100% is just 1. Like, percent just means over 100, right? So you know that like 75% means 75 over 100. So like 75% as a decimal would be 0.75. And so that means multiplying by 100% is just like multiplying by 1. And so let me just erase that little part of it. And this is my equation. Whenever I have theta equals 0 and c equals 0, then this first factor becomes 1 minus 0, because the theta is a 0, or 1. And then this would become 1 minus 0, because c would be 0. And so 1 times 1 is 1. But if theta is greater than 0, or if c is greater than 0, then whatever I get is less than 1. So actually, there's not really much of a contour line at p is equal to 1. There's only one single point that gives you p is equal to 1. The only point that gives you p of 1 or 100% is when theta is equal to 0 and c is equal to 0. So there's not really a contour line there. So the next thing we can do is, let's think about p is equal to 0 then. So I put in 0 for p. I have two factors here, and so this right side of the equation is equal to 0 if this is 0 or if this is 0. And for this first part to be 0, that's true if theta squared happens to be 2 times 180 squared over pi squared. Right? Because if theta were 2 times 180 squared over pi squared, then all of that stuff would cancel and I would have 1 minus 1, and 1 minus 1 is 0. But this over here would be 0 if c were equal to 2. So let's see if either of these are actually if either of these might actually happen in any sense. What would be 2 times 180 squared over pi squared? 2 times 180 squared divided by pi squared. 2 times 180 squared over pi squared. So that is 6,565. Okay, so then what would theta have to be? If that's theta squared, theta is going to be the square root of what we just found, which is 81. And so if we think about the globe really quick, and here's my little Earth, this is the North Pole and this is the South Pole. Again, I said the equator is when theta is equal to 0, and the poles would be when theta is equal to 90 degrees. So 81 degrees would be like right here-ish. And so we're basically saying if you're installing a solar panel that close to the pole at 81 degrees or above, then you're like not going to get any sunlight on that solar panel. It's not going to produce any power. So that makes sense. But the other part of this where it says c is equal to 2, if I wanted to make the second factor equal to 0, c would have to be 2, so I'd have 1 minus 2 over 2 is 0. Well, c is the fraction of the daytime that direct sunlight is obscured by clouds. So the C value has to be between 0 and 1. 0 when you never have any clouds. 1 is when you have constant clouds. You can't ever have 2, right? You can't ever say 200% of the time we're obscured by clouds. And so this is nonsense. That doesn't make any sense for us. So really, the only contour line that corresponds to P is equal to 0 is the contour line theta equals 81 degrees. Okay, and lastly, this is the least interesting case, but also the easiest for the same reason. If you wanted to write the equation for a contour line when P is equal to 0.5, just pop in the 0.5 for P. And there's a whole bunch of thetas and C combinations that will give you P equals 0.5. You can choose any theta here and set that theta. And then you would just have one equation with one unknown, the unknown being C, and you could solve for C after you specify theta. Or vice versa, you could specify the C value you want, and then you could always find a theta that matches that C value in this equation. So in question 3, ask what does the trace of this function along the line theta equals 0 looks like? And so what that means is I just take my equation from before that we had, P is equal to 1 minus all of this stuff, but I'm going to actually plug in the value theta equals 0. So when I set theta equal to 0, that all becomes 0, and this is just 1 times 1 minus C over 2. So simplifying, that's like negative 1/2 C, negative 1/2 times C plus 1. So this is the equation for a line. With slope negative 1/2 and y-intercept 1. And so this is kind of what the trace of that function looks like. As your C value goes from 0 to 1, your P value goes from 1 to 1/2. That's what we mean by the trace. You just set one of the values of your independent variables, and then you see what is your new single variable function that you're left with. Okay, so what if we set C equal to 0? Then my P function is going to be 1 minus that pi squared theta squared over 2 times 180 squared. And then this would be 1 minus C over 2. But if I set C equal to 0, this is 1 minus 0, and multiplying by 1 doesn't really do anything. And so this would be my function here. And this would also be a line where, no, it's not quite a line, it's actually a parabola. So I'm going to have this leading coefficient negative pi squared over 2 times 180 squared. And then I multiply by theta squared, which makes it a parabola, and then plus 1. So this, if I make a P theta plane, when theta is equal to 0, this is going to have P of 1. And then as theta increases, this is going to be a downward facing parabola because I have the theta squared. And this leading coefficient is negative, so that makes the concavity of my parabola down. Okay. Questions about this little quiz here? Again, what we talked about last week on Thursday is just the fact that you can have multivariable functions. And this would be a function that gives you the dependent variable power as a function of two independent variables, which would be the degrees latitude and the c fraction of cloud cover. And so some interesting questions we can ask about multivariable functions are, first of all, can you evaluate the multivariable function? Like in question 1 of this quiz, all we had to do is just plug in values for theta and c. That was it. It was just evaluating the multivariable function. Another thing that we like to do with multivariable functions is talk about the contour lines. So contour lines is just a path on your surface that has the same elevation or the same value of your output variable everywhere along that contour line. And then the other thing that we just mentioned briefly at the end of Thursday is traces. And so a trace is just a single variable function that you get if you set one of your independent variables equal to a constant. So then you just have your dependent variable as a function of your one remaining independent variable. And so that's what questions 3 and 4 were like. So today we're doing section 14.2. We're talking about partial derivatives, and partial derivatives is a way to apply derivatives to multivariable functions. Right, so we're just extending our definition of derivatives here. So when you have a function that's a function of two independent variables like x and y, and you want to take the derivative of that function with respect to just x, we say that you're taking a partial derivative. So this little symbol right here, we're going to call it a del. It's del. And it's kind of like a Greek lowercase letter delta, except really the Greek lowercase letter delta is like that, and this is like that. So I don't know. It's just a weird symbol that we introduced for partial derivatives. If we take the partial derivative of f with respect to x, what we're going to do is we're just going to pretend that y is like a constant, right? Just for pretend here. We know that y is one of our variables, but just in the context of taking the derivative with respect to x, we just sort of ignore y, and that we're like pretending that it's like, imagine y is the number 7, right? And the derivative 7 squared would go away. The constant would just vanish in the derivative. So we take the derivative of x squared as 2x. And likewise, if I take the partial derivative with respect to y, well, I just pretend that the x is a constant. And so in taking the derivative, the constants vanish, and then the derivative of y squared would be 2y. So example 1 says, evaluate the partial derivative with respect to x of the following function at the point 1, 2. And so where I'm writing 1, 2, I mean that's going to be my x and my y value. So x is 1 and y is 2. So if I want to take the partial derivative of z with respect to x, well, I'll go term by term and say this partial x with respect to x squared is going to be 2x. The partial derivative with respect to x of negative y squared, well, I'm just going to pretend that y is a constant, and that goes away. I don't have to worry about that. Where I have plus 3xy, well, the 3 is a constant, and I'm also going to pretend the y is a constant, and the derivative of x with respect to x would just be 1. And so this is going to be my partial derivative with respect to x. Then whenever I evaluate this partial derivative of z with respect to x at the point 1, 2, this is going to be 2 times 1 plus 3 times 2, because I just plug in 1 for x and 2 for y. And so this partial evaluated at 1, 2 is going to be 2 plus 6, that's going to be 8. Once you get that copy down, try the example below it. Try example 2. So in example 2, we're doing the partial derivative with respect to y. So partial z partial y is going to be I haven't done that part yet.
Wait, actually, I forgot the negative. And then we can. Negative 3.
So y is going to be 0, and x is going to be negative 1. So my answer is going to be 0 minus 3. It'll be negative 3. Okay. Do you have questions about example 1 or 2? Okay. Then you remember that whenever we were taking this, just the single derivative of a single variable function, we said that the derivative is the slope of the tangent line to the curve representing the function at some point. So whenever you have a function or a dependent variable z that's a function of 2 independent variables x and y, we're going to say that the partial z with respect to x is the slope of the tangent line to the surface that's given by that function in the x direction. And if you take the partial of z with respect to y, that's going to be the slope of the tangent line to the surface, but in the y direction. Let me try to pull up a graph to try to illustrate this a little bit. What is that? Oh, this is actually working today. Okay. So, this is what I tried to show you guys on Thursday, and it wasn't working. But let me do 1 plus x squared minus y squared. Let's see what happens. Okay, so that's a little bit obnoxiously tall. Let me scale this down by like a factor of like 4. There we go. All right, so I don't know if it's super clear what this is, but it should be like the shape of like a Pringles chip, or maybe like a horse's like saddle. And what I mean by like the slope of a tangent line is like, imagine you had a line that is sitting on the surface at one point. Like it intersects the surface just at one single point. It has the same slope as the surface, but the line is only going directly in the y direction. Like it's parallel to the y-axis. That slope of that tangent line, that would be the partial derivative of this function with respect to y. And then likewise, if you imagine a different line that intersects the surface somewhere at one point, it has the same slope, so it's like a tangent line to the surface. But if that line is parallel to the x-axis, like it's only moving in the x direction, that slope of that tangent line would be the partial derivative of this function with respect to x. So just like the derivative of a function was larger whenever you had a steeper curve in the plane, the partial derivatives are going to be larger whenever your surface gets steeper. The partial derivatives are sort of like the steepness of this curve, but the deal with the partial derivatives is you have to specify, am I talking about the direction parallel to the x-axis, Am I talking about the direction parallel to the y-axis? That's what it means to take the partial derivative with respect to x or y. I'm talking about how steep is the surface in the direction parallel to one of my x or y axes. If you imagine this as like, I don't know, like an area between two mountains, and you're like a hiker trying to climb up the mountain, if your partial derivative is greater, that means it's going to be a steeper slope for you to try to climb. If your partial derivative is like a negative number, that means you're going in a direction that would be like sloping downward. Okay. So this surface, z equals 1 plus x squared minus y squared, that's actually going to look quite a bit like this shape does. And so the question asks, what is the function that describes the line tangent to the surface in the y direction at the point x is 1, y is 2? And so what you would do is you would say, well, when x is 1 and y is 2, that point is going to be on my slope somewhere like right here. And if I only look at the way that this curve is sloping in the direction parallel to my y-axis, that's what I'm going to get if I evaluate this partial derivative. I'm talking about what is the slope of this curve in the y direction at the point x is 1, y is 2. So I'm judging based on this visual. I think it's going to be negative because this curve seems to be going down as I move in the positive y direction at that point. If I were moving in the positive x direction, it looks like it would be positive at that point, because as I move towards the positive x-axis, the slope is going up, but then as I move towards the positive y-axis, the slope is going down. So your partial derivatives are going to be different here. Okay, let's try. So I'm talking about the partial of z with respect to y. And if this is my function, z is equal to 1 plus x squared minus y squared, then the 1 goes away in the derivative because it's just a constant. I also don't care about the x squared because I'm pretending that x is a constant, and so I should get negative 2y. And if I evaluate that at the point where y is 2, then the partial of z with respect to y evaluated at the point 1 comma 2, that should be negative 4. So sure enough, we got a negative partial derivative with respect to y, because as I move in the positive y direction, my surface is sloping down. Just for kicks, let's pretend that we're looking for it in the x direction. And I'll be talking about partial z, partial x. And that would be 2 times x. And whenever I evaluate this at the point 1 comma 2, that would be 2. And that is a positive partial derivative with respect to x. So that means if you're moving in the positive x direction, then the value of the slope is going up. You'd be climbing up the mountain.
Thank you.
Bill, stop me if you have any questions. This isn't making sense so far. And another thing I like about this, but it might be a little bit hard to see, is that this curve itself has a little grid on it. Do you all see the lines that are horizontal and vertical on the slope? So one way that I like to think about these partial derivatives is if you found one of these lines on the curve that's actually parallel to the y-axis. Each of these lines on the curve is either parallel to the y-axis or it's parallel to the x-axis. The partial derivative is telling you the slope of that little line as it's locked into some constant value in one direction. Okay. So just like regular derivatives, single derivatives of single variable functions, we interpreted those as rates of change of something over time. Same idea with the partial derivative. Whenever we talk about acceleration, acceleration is the change in velocity with respect to time. And this velocity function over here, if I distribute this big chunk to 8 and I distribute that big chunk to the negative t, I'm just going to simplify this by multiplying it out. What I would get is c times 1 minus c plus 1 all times 8, and then minus that t times c times 1 minus c plus 1. So if I'm trying to take the partial derivative of this v function with respect to t, well, this first chunk, I mean, that is going to go away because that's all just a constant. I'm pretending c is a constant because I'm taking the derivative with respect to t. And then for the second bit, the derivative of t with respect to t is just 1. And so what I'm left with is going to be negative c times 1 minus c plus 1. My next question says, what is the effect of increasing caffeine intake on her speed when t is equal? Sorry, I didn't finish the previous question. So the previous question says, what is this acceleration whenever c is 0 and t is 2? Well, I actually don't have any t's left, but whenever c is 0, this would be 0 times 1 minus 0 plus 1. So it would be 0 plus 1. It looks like it would be negative 1. So that means if she's had no caffeine that morning and well, I guess it really doesn't matter how long she's been running. If she's had no caffeine that morning, every additional amount of time that she runs is going to decrease her speed by a rate of negative 1. So it'd be like, just giving units to it, would be like negative 1 miles per hour per minute or something like this. I really didn't put units on this intentionally because I didn't want to think about it. But that means she's going to be decelerating as she runs. As she runs more, her speed's going to slow down because her acceleration is negative. Okay, so then the next question says, what is the effect of increasing caffeine intake on her speed? So increasing caffeine intake, we're asking the question, how is our velocity changing with respect to caffeine intake? So I would write the partial v over partial c. I'm saying if I want to increase my caffeine intake by just a little bit, how would my speed increase? So it's this rate of change. And again, going back to this v equation, I'm going to write it out again. C times 1 minus c plus 1 times 8 minus t. Whenever I'm taking the partial derivative with respect to c, I'm going to pretend that that t is a constant. And so this is just going to be some constant multiplier. For this other part of the v equation, I want to go ahead and multiply it out, simplify a little bit. So I'm going to have c minus c squared when I distribute the c plus 1 times 8 minus t. And if I distribute that 8 minus t to everything, I would have 8 minus t times c minus 8 minus t times c squared plus 8 minus t. Just distributing again. So then my partial derivative of this crap with respect to c, well, I don't care about the 8 minus t on the end because this is just considered a constant when I take that partial with respect to c. If I take the partial of this first term with respect to c, that should just be 8 minus t. because the derivative of c is 1. And then when I take the derivative of the second term, that's going to be minus 2c times 8 minus t, because the derivative of negative c squared would be negative 2c. So let me evaluate this. Whenever I have c equals 0 and t is equal to 0, that would be 8 minus 0 minus 2 times 0 times 8 minus 0. And so it looks like it would be 8. And that's just to say that you would have a positive increase in speed if you consume a little bit of caffeine, if you haven't already taken any caffeine and you haven't started running yet for the day. Sorry, that example ended up being a little bit more convoluted than I wanted it to be. Y'all are my guinea pigs. Y'all are working these made-up examples for the first time. So the next page talks about higher order partial derivatives, and there's a little bit of new notation this time. So if I'm talking about the partial derivative of f with respect to x, another way that people like to write this, and you would see this in your textbook too, is you write f with a little subscript x. And that little subscript just means take one derivative with respect to x. And so you have the same situation if you're taking the partial with respect to y. That's how you would write it. If you want to take the second partial derivative, and just like with derivatives, we could take second derivatives. You just take the derivative of the derivative. You can also do second partial derivatives. You just take the partial derivative of the partial derivative. So if I want to take the second partial derivative of f with respect to x, I would take the partial derivative of f with respect to x, and then I would want to take the partial derivative with respect to x of that derivative. And the way that you could write this, and again, my shortcut notation is just write 2 x's in that subscript. That tells me to take 2 partial derivatives with respect to x of that function. Same thing for y. And then another thing that we have that's brand new for multivariable functions is that I might want to take the partial derivative with respect to x of some function, and then with the function that I'm left with, I might want to then take the partial derivative with respect to y. And so my shorthand notation for that would be f subscript x, y, and that tells you take the partial with respect to x, and then whatever you're left with, then take the partial with respect to y after that. And it turns out that the order that you take those doesn't matter. So that means the partial with respect to x and then y is the same thing as if you take the partial with respect to y and then x. And so your textbook has this nice tree, and I think it's worth showing that if you start off with your function and then you take the partial with respect to x, we call that fx. And if we take the partial with respect to y, that's fy. If you then take the partial with respect to x of that function, you would get fxx, the second partial derivative with respect to x. If you take the partial with respect to y of that function, you'd get fyy. If you take this function, fx, and we take the partial with respect to y, then we would get fxy. And if I start from that function and I take the partial with respect to x, I'd also get fxy. And we can keep going, right? Like we could do the partial with respect to x of that and get fxxx, the third partial derivative with respect to x. If I went over here and took another partial with respect to y, you get f y, y, y. If I started from here and I took the partial with respect to y, I could get f x, y, y. If I started from here and I took the partial with respect to y, I get f x, x, y, and then so on. That would be the same, and that would be the same. So if you have some goal, like if you say to yourself, I really want to take the third derivative of this function, one of my derivatives is going to be the partial with respect to x, and then the next two are going to be the partial with respect to y. There's actually multiple ways to calculate that. You could say, I'm going to calculate this derivative, and then I'll calculate this derivative, and then that derivative. Or you could say, I'm going to go here, and then here, and then here. Or you could say, I'm going to do this, and then this, and then this. And that's it. That's all your options. But you have 3 different ways that you could calculate any, well, some of those third derivatives. But hopefully you guys see how all these things are related to each other. And again, the really important theme here is that the order in which you're taking these derivatives doesn't matter. Okay. So this example says, find all first and second derivatives of the function. And so all first and second derivatives, that would mean taking, I want f x, the first partial with respect to x, the first partial with respect to y, the mixed partial, f x y, and also the second derivative with respect to x and the second derivative with respect to y. That's like the whole, all first and second derivatives, right? That's what we're asking for. So f x, if I just look at the derivative with respect to x of that function, well, this would be 15x squared. This would be minus 8xy, again, pretending that the y is a constant here, since I'm taking a derivative with respect to x, and then plus 3y squared, because I'm again pretending that y is a constant, derivative of x is just 1. I'm going to skip the minus 2y cubed, because if I pretend that y is a constant, then that whole term is a constant. 6 is a constant, so I ignore that, and I have minus 14xy squared. Then if I want to take the partial with respect to y here, my second term gives me minus 4x squared. My third term gives me plus 6xy. My fourth term gives me minus 6y squared. And then my very last term would give me minus 14x squared y. What if I want to take the second derivative with respect to x? Well, I just start from my first derivative with respect to x, and then I take another derivative with respect to x. And so this would be 30x minus 8y minus 14y squared. What if I want to take the mixed partial fxy? Then I'm going to start from fx and take the derivative with respect to y, or I could actually start from y and take the derivative with respect to x. It doesn't really matter. And so let me start from here and take the derivative with respect to y here. So the first term goes away, the second one becomes negative 8x, the third term here becomes plus 6y, and then the last term becomes minus 28xy. What if I started from here and now took the derivative with respect to x, well, that would be minus 8x for the first term. In the second term, I would have plus 6y. And then in the last term, that would give me minus 28xy. But just like I promised, the mixed partials are the same, regardless of what order you took those derivatives in. And stop me if you have any questions. This is a good example because there's a lot of different terms with a lot of different powers. Make sure you see how each one of these derivatives was taken. The one thing we haven't done yet is the second derivative with respect to y. So I just start from fy and take the derivative with respect to y, and that's going to give me 6x minus 12y minus 14x squared. Okay, so number 6 says evaluate g x x y at negative 1, 1. So that means after I find what is g x x y, I'm going to plug in x equals negative 1 and y equals positive 1. But in order to find g x x y, I'm first going to have to compute a second derivative leading up to it. And so there's a bunch of different ways I could get there. I could either do xx and then take the derivative with respect to y, or I could do g xy and then take the derivative with respect to x, or I could do actually yx, because that's the same thing, and then take another derivative with respect to x. So either one of those would get me there. But let's just, for the sake of it, do gxx. And then before that, I'll need to find out what is gx. So taking the derivative with respect to x of this function, well, x cubed becomes 3x squared. X squared becomes 2x, so this will be minus 4xy. 3xy squared is going to be plus 3y squared, and then the last two terms would be considered constants when I'm taking the derivative with respect to x. Now I need to take the derivative of that with respect to x. That will become 6x minus 4y. That last term would be considered a constant. Then I need to take the derivative with respect to y here, which was going to be negative 4. And it turns out that that's negative 4 regardless of what x and y are, because it's no longer a function of x and y. So turns out that that third derivative ended up being a constant function. Okay, so now I have h as a function of x and t. So h is going to be my dependent variable, x and t are my two independent variables. And I'm going to want to evaluate hxt at the point where x is 2 and t is 5. And so I'll need to find what is that mixed partial. I'm also going to need to find one of the single derivatives. Like we'll just do x first, but you could do t first and then do the derivative with respect to x. We're going to start off by taking the derivative of this function with respect to x, and that derivative will be 5 plus t minus 2x. So if the term was a constant, like the constant 3, or if a term only has t's in it, it goes away because we're considering t to be constant there. And then we're going to take this and then move on by taking the derivative of that with respect to t. And so that's going to be 1. And again, that's a constant function, so it actually does not matter what x and t are. That mixed partial is always going to be positive 1. Those were kind of boring examples. Let's talk about example 8, because that's an exciting example. So I have a function q. It's a function of the two independent variables x and y. And it's e to the power x divided by y plus x times y. And so in the end, I'm going to want to evaluate qxy when x is 3 and y is negative 3. So I'll need to first find what is qxy. Before that, I'll want to find what is qx. And that's just the derivative of this function with respect to x. So I'm going to pretend that 1 over y is a constant here, because I'm taking the derivative just with respect to x. And so the derivative of e to the x with respect to x is e to the x. So nothing new. And then where it says plus xy, I pretend y is a constant, and taking the derivative of x is just 1. Now I need to take the derivative of that thing with respect to y. And so I'm pretending that x is a constant, so that means e to the power x is just a constant for all I care. And this 1 over y is going to be y to the negative 1 power. And so whenever I take the derivative with respect to y here, I'm going to bring down the negative 1 and then make that negative 1 to a negative 2. So this is going to be negative y to the negative 2 power e to the x. And then the derivative of y will just be 1. So last line says I need to plug in x equals 3 and y equals negative 3. So I have negative 3 to the negative 2 power times e to the power 3 plus 1. So negative 3 to the negative 2 power, that's like saying 1 over negative 3 squared. Negative 3 squared is positive 9. So that'd be negative 1 over 9 times e to the 3 plus 1. And you remember e should be in your calculator. But e is like 2.718. And if I cube that, I have like 20.1. I'm going to divide that by 9. And so that's going to be that times negative 1 plus 1. So my calculator tells me this is like negative 1.23. Example 9 says find all first and second derivatives. So all first and second derivatives, that means I want to find the derivative with respect to x, the derivative with respect to y, the second derivative with respect to x, the second derivative with respect to y, and my mixed partial derivative. So if I take the derivative just with respect to x, the derivative of my natural log function is going to be 1 over whatever is inside my natural log function, so 1 over y minus 8x. And then my derivative chain rule says multiply times the derivative of the inside function. So the derivative with respect to x of y minus 8x is going to be negative 8. The derivative of my function with respect to y would be pretty similar, because the derivative of natural log is still 1 over y minus 8x. But the derivative chain rule this time is saying multiply times the derivative with respect to y of your inside function, but the derivative with respect to y of y minus 8x is just 1, because we pretend that x is a constant. Yeah. So far so good. If I want to take the second derivative here with respect to x, I'm going to keep my negative 8. And then I'm going to rewrite this just a little bit so that I can make it easier on myself to take the derivative. This is going to be like y minus 8x to the negative 1 power, because it's in the denominator. And so my power rule would tell me to bring down that negative 1 in front. So instead of a negative 8, that would make it into a positive 8 when I multiply by negative 1. And then I make that exponent into a negative 2, because the derivative power rule is that you subtract 1 from your exponent. So this would be something like 8 divided by y minus 8x all squared. And I think I forgot something. Yes, I did. I forgot my derivative chain rule. So chain rule says multiply times the derivative of my inside function. Well, my inside function is y minus 8x, and so the derivative there is going to be negative 8. And so this is going to be negative 64 when I do 8 times negative 8. Now divided by y minus 8x squared. So the partial with respect to y, I could write as y minus 8x to the negative 1 power. And so whenever I take the second derivative with respect to y, that's going to be a negative 1 times y minus 8x to the negative 2 power. And again, I don't have to worry about the chain rule here, because the derivative of y minus 8x with respect to y is just 1. So this is negative 1 over y minus 8x squared. And last but not least, we have my mixed partial. So let's start from the derivative of f with respect to y, and then let's take the derivative with respect to x. The other way we could do it is we could start from the derivative of f with respect to x, and then we could take the derivative with respect to y of that, and either way, it should give you the same thing. It's a good way to check your work, by the way. If I ever ask you for a mixed partial on your final exam, a nice way to check your work would be to do it both ways. Take both paths to get to the mixed partial derivative. Make sure you get the same thing. And again, taking the derivative of this thing over here with respect to x would give me negative 1 times y minus 8x to the negative 2 power. And now I have to remember derivative chain rule and multiply that by a negative 8, because the derivative of y minus 8x with respect to x would be negative 8. So that's chain rule. So the negative 1 times the negative 8 would be a positive 8. And I divide by y minus 8x squared.